Is my screen visible?
Yes, sir.
Okay. So let us start with our this last week assignment solution, and then let us move or discuss what are the queries you people are having, such that we can get it. Because we have one more week after that. What's the actual exam date of your paper? Hello,
29th.
29. Okay, so 24. Okay. If possible, I can give more practical practice question also. I will try. Okay.
Yes, thank you.
So let us start our assignment. Yeah, these are not this week assignment does not have much numericals. Only most of them are conceptual based questions. So let's start with our yeah. In this kind of question, actually, you have to be worried about. They will ask like that. Which among the following statements are true statements? Sometimes they will ask like which is false statement also. So suddenly, if you have a confusion that whether it is a true or false, yeah, that has to be you have to a little bit care because I saw this kind of questions in our previous assignment also. Sometimes they will say true. The similar way at bottom we are going to encounter another question which is not. So yeah, you can start our question. Which among the following statements is or are true statements? So we have given four options. It's like a comparison between standard camera imaging as well as a holographic imaging. So image taken using a standard camera contains face information. B. A hologram is an interference pattern. C. A hologram can be used to reconstruct intensity as well as phase information. D. A hologram contains the same information as that in that image taken using a standard camera. So you are supposed to select it whatever the correct answers. So people are already knowing what actually a normal camera will capture. That's actually we dealt with during our imaging the standard when we dealing with that imaging conditions in a normal camera actually there will be some optical element, usually it's a lens that will focus each point from the object in a 1:1 ratio. All the light, yeah, you have to take care, all the light coming from one point of an object is focused at a same point on an image plane. So, like that way, they are constructing an image in the case of a normal camera. A normal camera, what actually they are recording? They are actually recording intensity. Either it's a camera photographic plate or it's a CCD or the CMOS detector. It is actually responsive to the intensity of the light. So, intensity is actually amplitude square. So, if you are considering the light as an electromagnetic radiation, it is a complex. It has a complex structure which containing an amplitude part as well as a complex imaginary phase part. When you are getting a intensity portion, intensity is actually a modulus of your electric field. You can say it's like E square or mod E square. In that time, actually, you are losing your phase information. So, in a normal imaging technique, you will get only the amplitude information. Phase information is gone. So, the first question, first option, image taken using a standard camera contains phase information. That's actually wrong. You are not getting any phase information using a standard camera. Next, a hologram is an interference pattern. You people may have already gone through a how the holographic system is working. So it is actually if you're looking a hologram, you cannot differentiate. It's like a, whether it's like a interference pattern, it will be like a complex structure. If you see a normal hologram in your normal eye, if it's used with some particular wavelength, and if you saw with a normal eye, you may not even distinguish whether it's a proper hologram itself. So because it is actually a interference pattern of light coming from an object as well as a reference beam. So that's a complex structure of the hologram. So that option B is actually correct. So a hologram can be used to reconstruct intensity as well as the phase information. This is actually the purpose of the hologram. If you record the intensity information in the form of a diffraction pattern on the hologram, and you illuminate that hologram with the same or similar kind of reference beam, what you are going to reconstruct, you are going to reconstruct almost the amplitude information as well as the phase information of the object. So C is actually correct. A hologram contains the same information as that in the image taken using a standard camera. That's correct. No, the hologram does not contain the information like as is in a camera, because the camera image actually containing intensity information. A hologram, as a hologram, actually it does not containing any. It's actually interference pattern. From the hologram, you can reconstruct and get the amplitude as well as the phase information. It is not like a 1:1 image like intensity information like a camera. So the appropriate answers are B and C. Okay, and out. No doubt. No?
No, sir.
Now, yeah, these are actually conceptual questions. You have to get a normal concept of how a hologram works. What are the two processes involved in a holographic image? These are like it's a direct question. Anyway, okay. For coding sake, I will just pause. You may have seen hologram, na? You know what is a hologram? Do people know hologram, na?
Yes.
Anybody have any idea? Not an idea about hologram? If it's there, you can tell, or you can see in like a new books or some products. You may see, or yeah, in your mobile phone, everybody mobile phone battery. I think yeah, that's the thing. Because after a long time, actually, I see a very good hologram. It was on the Nokia. When the Nokia phones are available, you can see that Nokia phone's battery containing a very nice hologram. You will feel exact 3D image in that. Actually, that hologram containing a lot of security features. So they itself will reveal like that way. So at a particular angle, you can see a particular marking in that particular hologram. So like that way, you can ensure the genuinity of the product. So that colored thing, that's actually a hologram. I think already know that one, so I don't need to explain much. So normal case, how a hologram is created, there will be a photographic plate, and you have a particular object. An object. So the thing is that there should be a laser source, and and the laser source you will split into. Depends on that optical apparatus you are using. Actually, you can split in two ways. So yeah, if I am using a some beam splitter, I can split it like a perpendicular manner, and using some mirror or something, I will, and some lens arrangement I will do. I will expand the beam, and I will make that it is all thing is actually illuminated into this source, and this light is actually will reach on the particular photographic plate. Here also using some mirror kind of arrangement and some beam expander, I will make a reference beam also. What you will get here, actually you are going to get a interference pattern between this the light which is coming from sample as well as the reference. So actually what you are going to get is a diffraction pattern. It is not a original image. In the case of a normal imaging, what you are doing, you will have a object, then lens, then there will be some photographic plate, such that the light which is coming from each point is actually reaching to the same point. So if a lot of light is coming from this point, it will again focus at a particular point, such that you will have a feel of that, not feel, image of that particular thing. Okay, so the light coming from the bottom also focus to the same point. But in the case of hologram, it is not like that way. So a light coming from here will actually pass here, 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 here. Similar way, light coming from this point will also go here, 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 here. So what we are going to get is like a lights from each point is actually reaching at the every point on the hologram. So your hologram containing, or each point of the hologram, you can say ideally containing the information of the all points in your sample. So if you cut a small portion of a hologram itself, that's containing that much, the whole information about your sample. Only the intensity may be a little bit less, because you cannot reconstruct a maximum light which is passing through this. Okay, so this is the way how you are recording a hologram. After that, what you will do, you will actually take the hologram and illuminate with the similar kind of a beam. So what will happen? The transmittance beam will produce a 3D image of your particular structure, and you can also see, and there will be some another order light, such that it will produce a virtual image of your particular substance also. So there will be two images. One is a original reconstructed image, and another virtual image. It is something like that. As per that diffraction, it will be so. But this virtual image will be exactly like how it is you are looking from that side. Okay. So corresponding to how that diffraction pattern is changing, corresponding to that one, you will have a virtual image of that substance, not substance, that object. Okay. So what are the two processes involved in the hologram? One is actually capturing the interference pattern, and second one is actually reconstruction of the image using the same kind of reference light. Okay. Capturing the negative image of a light sensitive film and developing it into a photographic paper. This is what kind of imaging? This is the old film type of imaging. Okay. Capturing intensity information on a sensor and applying digital signal processing techniques to display the image. This is the new CCD or CMOS type sensor type of imaging. Okay, these two things are actually normal photography. A and C are normal photography only. One is the normal film photography, and C is actually digital photography. And B, capturing the interference pattern and recording medium and reconstructing the image using a laser source illuminated thus recorded pattern. This is a normal your hologram holograph. Okay, third one. These are like, yeah, questions or direct question. So a hologram is recorded by interfering an object wave OX, O0 XY exponential e raised to j into delta XY, and a reference wave R of XY equal to R naught exponential j 2 pi Fy. This is actually the same equation of the light which you used in your class. The result is a hologram which transmittance is a TXY. This is then illuminated with a reference beam resulted in the following field. Okay. Now, which term results in the reconstructed object beam? This is a question. This already have discussed in the class. Now you people can tell. T0 R of XY. What is the information in R of XY is actually, what's R of XY here? What kind of beam? R of XY. You people can tell which is R of XY. You know how this O0 square plus O0 XY into R star XY plus O star X into R of XY is coming here? This is actually a complex multiplication of your amplitude of this your combined object wave as well as the reference wave. Okay, just tell. Hello. Here.
Yes.
Yeah. So O0 XY, O naught square XY. Just think that what will be the information inside that one. O naught square. If some square term is came, what is the meaning? If the square term is come, what will be the meaning? Can you just tell how the square is come?
Di- direction term won't be there.
Direction term will be there or will not be there?
Um, won't be there.
Yeah. Your phase information is actually lost. That's a direct information. How in the case of a complex number or a complex function, your electric field is a complex. So if it is the case of an electric field, a square term is coming means you lost your phase term, because the complex into complex conjugate is actually giving the normal square of that particular thing. So O naught square,
Okay.
got it?
Yes. Yes.
Yeah. So O naught O of xy is containing O naught xy into exponential j into delta xy. Just so it's like this is like object A. I'm saying that O0 of x y. This is a not a complex term, because now I am adding that exponential I. That j or I, it's not a problem. Okay, say delta of xy, something I'm writing like this. Okay, this actually is containing a complex phase information, but I have just make that what will be the modulus of square. So I am saying that I am taking the modulus square of this term. This is actually a amplitude information. I can say that intensity information will be. Can you just tell anything here? Modulus of oxy square will be how much? What will be this value? So O0 xy square. This thing will not be there. Why it is not there? This phase term will not be there here, or that will become 1. Why? Any complex number you can write in terms of a complex number I can write in terms of a r e raised to I theta. Okay, any complex number I can write in terms of this one. And what is the square of that one? Mod z square means z into z star. Okay, so r e raised to I theta into r e raised to I theta star. R e raised to I theta is r e raised to I theta only into r e raised to I theta star. It like r star e raised to I theta star. Okay, I'm making it very high elaborated thing. So here r e raised to I theta into r is actually a real number. So real numbers complex conjugate is that real number only. So it will become r e raised to I theta star. What is the complex conjugate of something which is coming I? You have to change the sign of the I. So it will be e raised to I theta star will be e raised to minus I theta. So now you see e raised to I theta is here, e raised to minus I theta is here. This will multiply to form 1. Then r is here, r is here. That will become r square into 1. Similar thing happening here. You see. Oh, this object wave is composed of one amplitude part and a phase part. This is O0 xy into exponential this complex phase information. So when you are going to take an amplitude or the intensity, your only this amplitude function square will be there. You lost the phase information in the form of 1. Okay. So now you go to your question and see which term result in the reconstructed object beam. So you want something regarding your object information, and it should be including your amplitude as well as phase. It should contain. Okay. Now you can see one term they are given T0 R of xy. R of xy is actually what kind of beam? R of xy is actually representing your reference beam. So if it's R of xy, you cannot give anything information regarding your object. So it can give only information regarding your reference beam. That will be like a plane wave, or it's like a normal illumination. It's like laser source. So D0 into R of xy cannot give any information regarding your object. Next, some beta factor into T into R of xy into O naught square xy. Here you can see that okay, some information about object is coming because it's like a O naught square is there, but there's a problem. So O naught square, what is that O naught square will be? Whether it containing any phase information, that we told now actually. O0 square
No phase.
will not have any phase information. So it will have some amplitude information, but which is actually dominating here. It will have a particular amplitude information, but here I said there is a R of xy. So R of xy is a reference beam. This is actually the reference beam modulated with the amplitude of your original sample beam, I can say. The reference beam is modulated with your sample beam. So, and sample beam's intensity information only it is containing. There is no phase information. So actually it is like a modified reference beam. Okay. So you will not have the proper information of your sample at that time. Next. So it is like a beta and this transmittance R naught square xy into O0 xy. Now, what will be the R naught square xy? R naught square xy is actually giving a intensity information of your reference beam. Your reference beam is a normal light, does not have any particular information, but that intensity is got modified by this O0 xy. This O0 xy is actually a beam. It does not have any square term, so it doesn't lost that phase characteristics. So now this is actually this O0 xy means your object wave is modified by this particular amplitude and other factor. So actually here you are getting a information of your object beam which is actually modulated with some intensity. So this will containing a particular information about your sample. Because of this modification, so there is a like a beta and there's a transmittance and this reference beam's intensity. Because of this one, actually you will feel that there will be some variation. It will not look exactly like your object. So there will be some intensity variation or some portion actually, yeah. Actually it will be like there will be some intensity variation because this is actually whatever you are going to get and this whole light including the phase actually modified with your intensity and other things like modified with your other reference intensity and the transmittance and the other factors like that. But you are getting a information about your object. So this is containing a objective. Other one, there's a similar kind of thing, beta t r square factor and containing a o star xy. O star xy will be actually it is also containing a information about your objective, but it is in the conjugated objective. So you will get a like a virtual image kind of thing in that case also. But in that virtual image also you can see your original features of that particular sample. So whatever you are seeing in a hologram, what kind of image you are seeing? You know hologram, na? You people see hologram. You people have already seen hologram, na? In some way or something.
Yes.
Even in your, I don't know if you have see old big bubble gum gave some a lot of stickers, which is like actually if you rotated that one, it will change the colored image on that one. That's actually a hologram. I don't know how many people are remembering that one. Whoever is in that day, yeah, you can say 90s kids may be remembering that one. I don't know how many people remembering that. Many people have a experience of that one.
I don't think that bubble gum I don't have this.
Okay, when you people are taking bubble gum, you didn't get any sticker kind of thing.
I don't think so.
We remember, sir.
Yeah, because yeah, that time we were it's like a very fascinating kind of thing. So that's actually a hologram. That's actually two types of hologram. So you will see when at a particular orientation only you will see one image and you rotated that one at a particular thing you will see another image. What they did actually, they constructed a hologram using two different objects and two different angles. They put the reference beam and put the holo made a hologram containing the interference pattern in the same manner, and like that way they did. Now my question is that what kind of image you are seeing there in a hologram when we are looking, whether we are looking a virtual image or a real image. That's the question. What kind of image you are seeing in a normal hologram?
Virtual.
Yeah. Any other answer? Any other answer? Somebody have? So whatever we are seeing actually a virtual image only, because we are not looking exactly at the same. We are not reconstructing the image with the, how they formed an image, and we are not at all actually putting the image at a particular plane also. Whatever we are seeing actually, if you look at the direction from how they made the hologram, and we are seeing if the light is coming in a proper direction, we are feeling that that image is there inside that hologram. So that kind of image is actually a virtual image. Okay. Now we can go to the other question. Now, a time domain optical coherence tomography system uses a broadband light sources, a light source with a high temporal coherence, a monochromatic light source, a light source with lower temporal coherence. These are so like these also direct questions. You people are already knowing that one. If you go through that class, actually you people may be knowing. Otherwise, go through the class such that you can understand. Okay. In optical coherence tomography, how you are going to create your image? There will be two beam split, a beam splitter. There will be a source, and from there it will pass to your beam splitter. From there it will go to one of your reference mirror, and to your sample. This is your layered sample, you can say. And okay, and the principle will be, when your path length of your reference beam is actually matching with the sample beam, only that particular plane will be undergo constructive interference, and you will get that particular image. Okay. If your mirror is at this position, and let it be, this is making a particular path length which is matching with the light which is traveling in this one. So you will get only the image of this particular plane. So you will create a particular image at that particular plane. What you will do? Then you will do this mirror a little bit away. And if the mirror is at this position, corresponding to this position, there will be another plane, and the interference will be happen only when that path length matches. Okay. So it will form image of this particular plane, and you will get that plane image also. Okay. So actually what you want, when you are moving the mirror, then only a particular path length condition is getting satisfied. Only at that particular position you should get an interference. If you are using a source which is having a long coherence length, so if the lens, if you have your mirror position at this position also, or this position also, if the source has a long coherence length, it can form interference pattern here also, here also, here also. It can form. Why? Because that light source property or the coherence of the light signal will not change fast, or it will not change within a short distance. So you will get a interference pattern for this whole surface, or the for the whole depth, even though if you are using a mirror, and even though you may not have to move your mirror, because the coherence length of your source is so high such that it can form a interference pattern in a very broad distance. That's actually good in the case of if you want some interference fringe. But now actually we don't want a very good interference at every point. We want only that particular plane should get imaged, or only that plane, the information from the plane should get as an interference pattern. So you don't want that much big coherence length. You want very short coherence length. So what is a relation between your coherence length and your uh, bandwidth of your beam? If you have a short bandwidth beam, means you will have a very strong coherence length, means a very long coherence. Hello, Moto. Okay, you got any idea? Or your broadband light source, what is the bandwidth of your light source? How the bandwidth and the coherence length are connected? I think this already had. Okay, people are hearing now.
Yes, sir.
What is mean by bandwidth of a light source? What is bandwidth?
Maybe the range of frequencies where it is emitting
Yes.
strongly.
Yeah. So how you will get that one? You have to take a spectrum of your light. So I am saying that I have three light sources. Okay, three similar kind of light sources. Because in our eyes, both, you may have seen this red 0 watt bulb which is in red color.
Yes, sir.
Red 0 watt bulb. Okay, this is my first light source. Okay, second light source is a red LED. Okay, third one is a red laser pointer. Okay, how the spectrum look like? I'm saying that all of them have some same wavelength. Okay, all are looking like a similar red. So I'm saying that all of them have a 650 nanometer. 650 nanometer. Okay, if you look the spectrum of your all three things, because everything is 650 nanometer. We'll see this as a red color, this is also red color, this laser also red color. If you look at the spectrum, so I am plotting my intensity in terms of wavelength. Here also I am plotting intensity in terms of wavelength. Here also I am plotting intensity in terms of wavelength. How it will look like? This normal lamp was, I'm saying that this is 650. This mid portion is 650. Mid portion is 650. Normal lamp will have something like a broad thing. Even though it is 650 at the middle, it will have a lot of another frequencies coming at the sides. You cannot differentiate at that time because the maximum intensity is coming from red, so you will see it as a red, but it is not a pure red. It will containing a lot of nearby frequencies. But in the case of LED, you will see that it is some more narrow. In the case of a laser, you may see that it's like it will have a very high intensity, but it will be like a very narrow. Okay, so this actually giving the purity of the your bandwidth, is actually giving the purity of your wavelength region. So it's a broadband source means it will have a lot of nearby wavelength. Narrow band means it will have less thing compared with the mid region. It's like a very short band. Laser will have very short band. So how it's actually related? You know the normal relation, na? C is equal to nu lambda, or lambda is equal to C by nu. This thing you know, na? Or you can write that nu is equal to C by lambda. So if you want that error, or that how this lambda has the width, you have to differentiate this one. So to take the differential of this thing, or take the differential of this one. So take d lambda will be equal to, so C by nu, 1 by nu, the differentiation of a 1 by something will be minus 1 by x square. Actually we are not dealing with any direction here, so it will be C by nu square delta nu. Or if you took a d nu, C by lambda square delta lambda. So just think this equation. So if you have a delta lambda, what is delta lambda? Delta lambda is actually giving the width of this one. So if the delta lambda is more, what will happen? D nu will be also be more. Okay, the width in frequency will also be more. Then what is actually d nu? How you can say d nu? D nu, you can say that d nu is 1 by delta t, or delta t is 1 by d nu. What is actually giving this one? D nu will have a particular value that's actually give a information about a time difference. What kind of time difference? This is actually given time difference at which how much time the light can travel without losing its coherence. So if you have a two light beam is traveling, and just think that it is also both started similar kind of thing, but yeah, after some time it is losing the coherence, because now you can see that the phase is actually completely opposite, and here you can get a total destructive interference. And at that point, if this much time the light can travel, this time is called a coherence time. and the coherence time is actually the reciprocal of your frequency bandwidth, and the frequency bandwidth is actually you can take as a function of your wavelength bandwidth. So if your frequency bandwidth is high, your coherence time will be lower. So you can see if the frequency bandwidth or the wavelength bandwidth is high, your coherence time will be lower. So it will have a less coherence. Okay. Now this is actually the relation between the coherence length. This is you are getting coherence time. Now multiply the coherence time with the velocity of light, c delta t. That's actually giving a coherence length. So this is, you can say that this much length, if you are passing it through the air, the light can travel without losing its coherence. So in the case of an OCT, you want what kind of beams? You don't want a high coherence length beam, because if you have a very high coherence length, at any point you are going to get the coherence beam, and the coherence beam always produce the interference pattern. You don't want the interference pattern at all point. You want only interference pattern at a particular point where corresponding to your reference plane adjustment. So you don't want a high coherence light, and the relation between the coherence as well as the spectral bandwidth is actually similar. If you have a bandwidth more, means you have a less coherence light. So you have to use a broadband light as well as a less coherent. Actually, they are actually same. You can say that it's a broadband light, means it will have a very less temporal coherence. It's a connected matter. Okay. So a light source with a low temporal coherence and the broadband light source, means these both are actually same only. So A and D are same. A light source with a high temporal coherence, you don't want that one, because it will produce interference pattern at all time. You don't want that. A monochromatic light source, what will happen in the case of a monochromatic light source? It will give only that particular intensity. So actually you want at different region of your normal OCT, optical coherence tomography. So whenever that particular wavelength or is satisfying that your particular phase condition, you will get a nice interference pattern. So actually you can get your resolution. Actually you are taking resolution more by adjusting your mirror. So you don't want any information other than you are adjusting your mirror. So in order to get all the information, in the case of a interference pattern, you don't want a high coherence length and high monochromaticity. Actually you want a broadband light source, means it will have a very less spectral purity and with a low temporal coherence. Okay. You are hearing now? I'm not seeing.
Yes, sir.
Next, when the reference mirror is moved in a time domain optical coherent tomographic system, which of the following statement are true? Now question. Though there are different reflection from different depth of the sample, the signal in interest is gated by the coherence length of the source. So this is the thing which we told. Though there are reflection from different depth of the sample, because you will have a reflection from your sample at a different depth. Here also you'll have, another one also you'll have, the more depth also you will have. But which one will only get a constructive interference? Only that particular beam which have a exactly matching with your particular mirror arrangement. You will have a different reflection from different sample area, but only that particular sample which is matching with your coherence length of your reference beam mirror arrangement will have a create the image. Okay, so your option A is correct. Next, the path difference between the reference arm and the sample arm is less than the coherence length of the multiple layers of the sample at the same time. The path difference between the reference arm and the sample arm is less than the coherence length of the multiple layer of the sample at the same time. Just think, what would happen if the path length is within the coherence length? The coherence length is the length within which the coherence property of the light is same. If the light has the coherence within the coherence length, so it can produce an interference pattern within all that length region. So if your path length is less than your coherence length, you are going to get a image irrespective of your mirror arrangement. If you kept it very near and that is within the coherence length, you are going to get a interference pattern. And if you move your mirror much far away but within the coherence length, still you are going to get interference pattern, because the light from your sample as well as your reference is actually always in coherence. So you don't want to use that one. So you don't want that much coherence. Why? This is a optical coherence tomography system. That's why you don't want to get that coherence. Because if you get a coherence, means that you are not going to get any information from your sample. Actually, you are going to get a nice interference pattern, but that will not give any information in your sample. But yeah, when we are doing our normal interference experiments, actually we wanted a very high coherence length such that we'll always sure about we'll get some interference pattern. But now I don't want any interference pattern. It's like only one interference pattern which is corresponding to my particular arrangement of my reference beam is actually I want. So this thing I don't want actually. So path length should not be within the coherence length. The path length should be less than your coherence length. Sorry, path length should be more than your coherence length. Or the coherence length should be much more less than your path length. That's it. The path difference between the reference arm and the sample arm is less than the coherence length for only a single layer of the sample at a time. Okay, path difference between reference and the sample arm is less than coherence length for only a single layer of that sample at a time. The interference amplitude will be varying for different depth of the sample. This actually, yeah, your sample have a different composition. So the interference, because you will get a maximum interference pattern only if your sample intensity from your sample as well as your reference beam are almost same. But if your sample is varying, you will get an interference pattern, but that interference pattern intensity will vary. Depends on your how much light is coming from your sample beam, because reference beam is going to be a constant. Okay. When the reference mirror moved to a particular position, the reflections of the sample is less than coherence length. Only a single layer of the sample at a time. At idiocity depths, then interference amplitude will be different at different depths. Okay. Next, intricate color patterns are seen on an oil slick on a wet asphalt pavement. You are seeing that yeah, nice interference colors in a oil films on a road. Which of the following statement cannot be true about the pattern? These are the things you have to see. Sometimes they will ask for which can be true and which cannot be true. Now, okay, how you are seeing a different patterns in a pavement. Just think that you have a yeah, you have a road, and above that one, yeah, usually in rainy season you will see, okay, and there's a water layer here. Above that one, there will be some oil layer. Okay, this oil layer thickness is not uniform. It will be different at a different point. So what happens is some light is coming, and actually what kind of light is coming? It's coming white light only coming. So it will have violet, it will have green, it will have red. All light is coming. Means it's a white light is coming, but and what happened? There will be a reflection from your top surface of your sample. It's an oil layer. This is a oil layer, and there will be a reflection from the bottom surface of your layer, thin layer. So now we see that with respect to the top surface, there is a extra path length is traveled by your light which is coming from your bottom layer. And if these lights are satisfied the condition for constructive interference, what will happen? You will see a bright light corresponding to that particular wavelength. And now you see this is a oil layer having different thickness at a different position. Just think that if red is satisfying a particular interference condition at a particular depth, similar position where the path length is actually same, you are going to get a red light at that position. And see some another point, maybe actually that constructive interference position is satisfied by green. So wherever the thickness is corresponding to that particular path length, your green is getting constructive interference. And some another portion, the same thing happen for violet. So depends on the thickness of your film, at a different part of the film, different wavelength is getting constructive interference. So you will see actually a colored pattern on your thin film or that oil film. Okay, this is the reason which you are seeing nice colored thing in your mm, oil droplets which is spilled on a road. Okay, this is the same thing they ask. So the thickness of the oil film satisfies the condition for the constructive interference for multiple wavelength at a different region of the film. That's actually true, but you don't want to take true option. You have to take the false option. So A you cannot choose. The thickness of the oil film satisfies the condition for constructive interference for only one wavelength at different regions of the thin film. If it's only satisfying for the only one wavelength, you cannot see multiple color on that particular thing. So actually the condition for constructive interference is satisfying with the different wave set, different position. Okay, the asphalt absorbs the transmitted light, preventing back reflection. That's actually true. Asphalt is actually, yeah, the tar. Like because of that tar, it will prevent the back reflection. So you don't want any back reflection. What happens if there's a back reflection? Your effective of your color pattern will not be that much good. What happens? Just think that this is a not a road. This is something like a white thing. So if it is something white, what will happen? The light which is transmitting beyond this thin film will also get reflect back, and this reflection is like a normal reflection from a mirror kind of thing. Not, it will not be like a very specular reflection, but yeah, it will be diffuse reflection. But actually this kind of light will decrease your visibility of your colored fringes on your thin film. Since this is a black thing, whatever is reaching down actually is getting absorbed. So the light which is reflecting from this surface will be very less. So most of the light will be reflecting from the top surface of your oil as well as the bottom surface of your oil, such that it will give a interference pattern and you will see a nice colored band. Okay, so you have to choose options D and D. Here they say the asphalt causes back reflection which result in the intricate color pattern. Actually, if asphalt is reflecting, then you will get a less intense colored pattern. Okay, next question. Yeah, now from here onwards your numerical things start. Okay, people are hearing now.
Yes, sir.
Okay, now we can go to the our numerical part. Okay, a soft film surrounded by air has a refractive index of 1.38. If a region of film appears bright red, 633 nanometer, in normally reflected light, what is the minimum thickness there? Okay, people can answer the question. Now what they given, they have a soap bubble of, so you will have a soap bubble having, will having a soap bubble having a particular thickness. You don't know the thickness actually. Okay, it's okay, let it consider it as a nice soap bubble. So what is the, now I am going to zoom this portion. Okay, I'm taking a zoom the portion of this particular portion. So how it will look like? Okay, what is the medium here? This position, what is the medium? It's actually outside of the bubble here. What is the medium?
Air.
Air. What's the medium here? Inside.
soap liquid?
Inside inside a soap bubble
Air.
here. Yeah. Inside also there will be air. So here at this interface actually there will be a thin layer of your soap water layer. It has a refractive index. They told it's like a 1.38. Okay. They are saying that it is appearing in a bright red color. Okay. So it is actually doing some interference on red color having a 633 nanometer. What is that meaning? That means if you put a light, it will reflect from this surface. Something will transmit to this surface. It will come back and it will reflect from this surface. Okay. Something may be transmitting here. We don't worry about that one. We are only seeing the bubble from outside, so we will see that what are the light which is coming from top and bottom. These are the things which is getting constructively interfere and producing a bright color. Okay. Now you see what are the light which is interfering here. One just reflecting from top surface. The other one is actually reflecting from, it's transmitted from top to bottom, then bottom to top, then it's coming out. Okay. This you got that idea you got na. These are the light which is getting interfered. There will be your soap bubble. This is your light is coming, and I'll put this is the reflecting. So first one which is getting reflecting here. The other one is going inside. If this is the thickness, I'm saying that D is the thickness. It is traveled D distance here, and it is again traveled one more D distance here. Then it is coming out. Okay. So how much total distance it is traveled? How much distance it is traveled? People are hearing now. I'm audible now. People are hearing. Whether I lost my connection or you people are hearing. Hello.
Yes, sir.
Yeah. Whether I lost my connection in between?
Audible, sir.
Yeah. Okay. Yeah. Then you can tell that how much distance this second ray traveled compared with your first ray. This initial,
Twice the.
yeah, twice the distance of your D. So it's actually traveled 2D extra with respect to your first beam. Okay. Then what will be the path length? What will be the path length of your light? What will be the path?
Refractive index to thickness of the.
Yeah, thickness we already incorporated 2 into thickness. For path length, one more parameter we have to incorporate.
Ref-
Yeah, we have to incorporate the refractive index of your particular sample. Okay, this is your film thing, refractive index. So the total path length is a 2dnf, but here actually you have to do one more information. So just think that if a reflection is happening from a low refraction index region like air to film, from low to higher, if the reflection is happening, there will be an extra pi phase difference happens at the time of reflection. Okay, if your light is moving from a rarer medium to a denser medium, it's like air to glass or air to water or air to some medium which have a refractive index more than compared to that of air. So in that time, if it is reflecting, the reflected wave will have a extra path phase difference of pi. 2 pi phase difference is corresponding to lambda path difference. Okay, so pi phase difference will be corresponding to a lambda by 2 path difference. Got it? Okay, so your initial beam will have a extra path difference of pi plus your this transmitted beam. This will go here, it will reflect from here, but whether the reflection is from rarer to denser or denser to rarer, it have a
denser. Yeah.
yeah 1.38 refractive index, and this will have a 1 refractive index. So denser to rarer refractive index does not have any particular path difference. Okay, if it's moving from rarer to denser only, it will have a path difference. So what will be your total path difference? The path difference which is caused because of this particular reflection, that would be pi phase difference. Corresponding to the pi, there will be one lambda by 2 path difference plus what will be the another path difference? The path difference because of your total distance. This is a 2dn. This will be your total path difference. Got it? And if that path difference is corresponding to lambda, you are going to get a bright band. Correct? If your total path difference is actually matching with your wavelength, so what will happen? This will combine to form a bright interference. Correct?
Constructive.
Yeah, it will go into a constructive interference. So your condition for your constructive interference is this one for this particular case. Okay, so what you can do, 2dnf, you can put it in lambda by 2, it will go other side, it will become 2dnf will be equal to lambda by 2, lambda minus lambda by 2 will become lambda by 2. Okay, so what you want to understand is d will be lambda by 2 into 2nf. So your d will be lambda by 4nf. Already given lambda is 633 nanometer divided by 4 into nf will be 1.3880. So What will be the value? 633 by 4 into 1.38. We 114.67. 114.67. Wait, got any doubt for that particular thing? You see, for the maximum reflection of red light, thickness d is equal to 2m plus 1 lambda by 4n. How these things are coming? This is actually coming by taking care of this one. Okay, this is the direct logically you can solve, but you have to make sure that if it is reflecting from here, yeah, coming from rarer to denser, the reflection will have a pi phase difference. Pi phase difference means a lambda by 2 path difference. And if it's like a reflection is happening from denser to rarer, there will not be any phase difference, so that you don't need to consider. But only at one position you are getting a phase difference of lambda by 2, and another position there will not be any phase difference, means you have to add that two phase difference together. Okay, okay. Any doubt for that one? Then I will ask one question. Just think that in the same condition, if the third layer, if this third layer is not air, if it is some glass, what will happen? If the third layer is not air, it is glass, and the soap bubble have the same thickness, whether you will get a bright fringe here for the red, whether you will get or not. It's the same thing. I have a, now we say that 114.67 nanometer. So it's like a, if my soap bubble have a 114.67 nanometer, and if this is air and this is air, I will get a red light will come here, one will get reflect here, one will get reflect here, and it will give a nice red light. If this bottom layer is not air and it is glass, whether I will get the same kind of red reflection from there or not, that's a question.
So again, that there's another pi.
Yeah, so what will happen? So this is air to glass, so actually I told that there will be a pi phase difference. This is from sorry, air to liquid, so there will be a pi phase difference. Here actually liquid to glass, glass will have much more refractive index compared to your soap liquid. So actually there will be one more phase difference, lambda by 2. So if you add together, that will be extra phase difference of lambda. If it's a extra phase difference of lambda, actually you don't need to consider that phase difference at all. Now think that if this thickness is 114.67, actually this thickness is actually giving a constructive interference for, if the including that particular phase difference of lambda by 2, not for the lambda. But if you put the same thickness and the glass there, what will happen? It will satisfy destructive interference instead of constructive interference. What you will get? You will see that if you put a red light here, red light never going to reflect back. So if this is a glass and you put the same thickness for the constructive interference for a bubble, you are going to get a anti-reflection coating for the red light actually. Got it? Because if you put, whenever you are going to put a glass here, there is going to be a extra phase difference. The corresponding there will be a path difference of lambda by 2, and this lambda by 2 and the top lambda by 2 will cancel. So what you are going to get is a anti-reflection coating. In the case of the bubble, it is forming a bright interference fringe, but whenever you put a glass at the bottom, you are going to get a dark. There will not be any image for that particular red. Got it? It's clear?
So why again lambda by 2?
What?
Why lambda by 2?
Because you are saying why the path difference is coming as lambda by 2.
Oh, okay, so I got it. Yeah.
Yeah, it's a phase difference of 2 pi is corresponding to a path difference of lambda. So pi phase difference means it will give lambda by 2 path difference.
Yes, got it.
Okay. So yeah, this kind of concept you have to be think. Sometimes you can see that in some equation they are saying that okay, something by lambda by 2 is giving constructive interference. Same way you can see that after some time they are giving that lambda by 2 same as a destructive interference. What is happening? Actually, there will be an additional phase difference of pi happening at somewhere there. That's actually you have to care. In this case, actually, the extra phase difference is happening in the case of air. Only one time, one portion you are getting a phase difference. So that's actually extra. If you are getting at the two sides same phase difference, actually you don't need to consider, because that two phase difference pi will added together to form 2 pi phase difference. If you are adding a phase difference of extra 2 pi, actually it cannot give any extra effect on that one, because 2 pi is exactly, it's looking like a lambda path difference, or it's like a zero path difference also. Zero path difference, lambda path difference, 2 lambda, 3 lambda, it does not have any extra effect. Okay. Now I'm going to the other question. Yeah, from that one actually this is a, I think this we already discussed. A spectacle lens made of ophthalmic crown glass is coated with a single layer of anti-reflection film which efficiently transmits a yellow green light. What is mean by the light will efficiently transmit a yellow green light? Means it will not allow yellow green light to reflect. It will completely transmit that yellow green light. That means that middle portion of your normal white spectrum. What color will the lens appear in the reflection when illuminated by a white light? So what happens in the case of if you illuminate it with a white light? It will transmit all the yellow green region. Means the middle point of the spectrum, it will completely transmit. Whatever will be reflecting the edge position. One side will be like a red, another side will be like a blue violet region. So it will be like a mixture of red and your blue region. What will be you will get it? You know that color combination, na? Red and blue. If you add it, what you get? You will get a magenta. Okay. Got? Do you have any doubt regarding that question? This is just a conceptual based question. Okay. Next, for 9th and 10th question, a glass substrate is having an index of 1.5 to be coated with a silicon nitride film to eliminate the reflection of normally incident light wavelength of 1550 nanometer. The refractive index of silicon nitride at this wavelength is 1.99. Now, again, you have to apply your logic here. A glass substrate having an index of 1.5. Okay, so coated with a silicon nitride with wavelength refractive index of 1.99. So you are having a glass substrate. Refractive index is 1.55. Okay. Above, we are going to coat with a silicon nitride having a refractive index of 1.99. Okay. Now, what will be the top layer? Top medium. What is the medium above these two constructs? This is glass. This is silicon nitride. What is the medium above this one? What's the top layer? People are hearing now. Okay. This is the question which is coming now. Can we call it subtraction of color from white light? Actually, yeah, you can call. There is no problem. Yeah, because the white light is actually composed of different compositions. So, if you are considering it as a combination of your white light, you can consider it as a combination of the primary colors like green, red, and blue. So, in that particular case, what's happening? The green is getting transmitted. So, only the red and blue part will be get reflected. So, whatever you are going to see in the case of a reflected image, only red and blue part will be there. So, red and blue will combine to form magenta. That's secondary color. So, you will get a magenta with a lot of bluish tint, because some violet color is there, that will also give much more effect. So it's like, yeah, you can call it as a subtraction, but yeah, it's actually, yeah, you can say it's like a differential reflection, you can say something like that, because only till a particular part will get reflected, the other part is actually get transmitted. But yeah, it's not like a mathematical operation to get subtracted, but yeah, only one part is getting reflected, other part is getting transmitted, and you are seeing that complementary color of that transmitted light you are seeing as a reflected light. Yes. So this question, The other one, next question. What what is the top layer? Top medium. There's a glass substrate. Above it, there's a silicon nitride coating, and above, what is the medium? And what is the refractive index of that particular medium? People are hearing that. Yes. Yeah. The medium is actually air. So, what are the two types of reflection is happening here? The light is actually coming from air to this film. Light is coming from air to film. It is getting reflected at the first phase. Then some portion is getting transmitted and reaching at that silicon nitride glass interface, and again it is reflecting, and that is transmitting, and it is actually getting interfered. So it's a similar way. Now you see that first reflection, this is the refractive index 1, then refraction index 1.99, then refractive index 1.55. So 1 to 1.99 there will be an extra phase difference of pi, corresponding to path difference of lambda by 2. Okay, 2 pi phase difference is corresponding to lambda path difference. So pi phase difference is corresponding to lambda by 2. Okay, so top region there will be extra phase difference of pi, that will give a additional path difference of lambda by 2 there, plus what are the path differences happening here? Now you see here there will be thickness of the silicon nitride. I am taking it as D. So it will pass through once, again come back. But here this reflection, this is 1.99, then it's 1.55. There will not be any path difference from this reflected beam. So only the phase difference will give that particular that particular, yeah, there will not be any phase difference at that particular interface. So only the contribution will be the path difference or the optical path. What will be the optical path? 2 times d multiplied by that particular wavelength, 2dn. So total path difference will be lambda by 2 plus this 2dn. Okay, any doubt? Now you have to get it satisfied with your condition for constructive interference or diffractive interference. So your question, you can see the question is, which equation should be used to calculate the required thickness of the film so that it acts as an anti-reflection film? So you don't want any reflection at the bottom or top. So actually there should not be any constructive interference by the reflected light. So you want a destructive interference by the reflective light. Okay, so what is the condition for the reflective interference? It should be an odd number multiple of your lambda by 2. The two waves which is actually getting interfere if the path difference between the two beam is an odd number multiple of lambda by 2, you are going to get a destructive interference. Okay, so this is the path difference which we calculated. So I want a odd number multiple, some 2m plus 1. I'm putting lambda by 2 here. then it will give a condition for my destructive interference. M will be a number. Okay. Now lambda by 2 plus 2dn will be equal to 2m into lambda by 2. It will be 2m lambda by 2 plus 1 into lambda by 2 lambda by 2. Okay. So this lambda by 2 and this lambda by 2 will cancel. 2, 2 will get cancelled. So 2dn will be some m lambda. Now this is actually condition for your destructive interference. So you want thickness. D will be some m lambda by 2n. Or if you take the first order one, then m should be 1. So it will be like a lambda by 2n. Okay. C. The answer will be lambda by 2n. This is actually coming because considering that two phase reference, here actually only one place your phase difference is happening at a air to thin film interface. There will be an extra phase difference of pi at that interface, but when it is traveling from your thin film to glass substrate, this is actually denser medium to rarer medium. There will not be any phase difference at that point. So you will not have a additional path difference. So only one path difference you have to consider and equate with your destructive interference criteria, and you will get this answer. Okay. Next is if you could pick a film with a specific refractive index, what value would be the best? So this actually, yeah, without derivation, I had actually solved that one. Actually, yeah, in order to match the intensity almost equal, the refractive index of the thin film or the middle film should be square root of or the geometric mean of the first two the layers which is at the two sides of the film. So this is your thin film. Bottom side is glass of 1.5. The top side is air of 1. So if you can choose the refractive index of the film, it should be square root of 1 into 1.5, and that answer will be 1.22. Okay.
Now, what is the meaning of specific refractive index here in this question?
What? 1 minute. Just see. If you could have film with a specific refractive index, the thing is like the before 90 they said that the substrate is coated with a anti-reflection film, which is they already said that it's like a silicon nitride. So if you're saying that you are going to coat with a silicon nitride, you don't have any option of taking a refractive index, because that if you decided the material will have a specific refractive index. But in the second question, actually they are giving you an option. You can take a refractive index. So just think that you will have a lot of material which have a different refractive index as much as you wish. In that case, what kind of material you will choose? That's a question. So it's like a there is no constraints. You can decide as per your wish. So in that case, which refractive index you will decide? That's a question.
What could be the another way to frame this question?
What could be the another way means now you see that now if they are saying that you have to coat that material with the silicon nitride. So it's in that first question actually they decided the refractive index. Then you don't have any option. You have to go with that particular material. Okay, that you understand. Na? So if they decided to make the question can come like this way. You have two substrate. Most probably that top substrate will be air. Bottom substrate can be anything. It can be sometimes a glass like a refractive index of 1.5, or it can be another refractive index like a plastic substrate which have a less refractive index. So the question can like a same question can like a double question like a, you are given two material, the top material and the bottom material. Now you have to put a thin film in between. You are given the option like you have to choose refractive index as well as the thickness. They can directly give like that. If you have the freedom to choose both, then you have to take a refractive index of the geometric mean of this two substrate, air as well as the bottom substrate, and you have to take a thickness of lambda by 4. This is a specific question. So if they are asking for like you have the both the option, like you have the option to take a refractive index as well as a thickness, then it's like a easier calculation, because in that case always the middle portion refractive index will come as the square root of that two refractive indices, and that will be always less than or in between your air and that substrate refractive index. In that condition, the condition for destructive interference will be lambda by 4 thickness. So it's like a direct question. So if you have the option to choose both, but if they already decided, if they said that thickness is specific, then you don't have any option. Then you have to find out how much path difference is coming, because the thickness they define. It's not the you deciding. So based on the path difference, you have to see which wavelength can be used as an anti-reflection, or which wavelength will be completely omitted from reflecting, or which wavelength will be transmit more. This kind of question can come. So same kind of thing, instead of asking anti-reflection, they can say that which light will transmit more. So which light is actually getting reflected less will transmit more. So instead of the question like a, you want to make an anti-reflection coating, the same question can come like that way, which is the maximum transmitting wavelength they can ask. Similar way the question can be framed.
Maximum wavelength transmittance.
Yeah, the
Mhm.
wavelength which is getting transmitted maximum. So this will also the same answer as which wavelength will be reflected least, because which wavelength is reflecting least will transmit most. In that case also you can define thickness as well as the wavelength or refractive index. The three things: wavelength, refractive index, and thickness. These three things are the parameters which is coming here. Always you have to take care that yeah, from rarer to denser when light is traveling and the reflection is happening, then there will be a extra pi phase shift in the reflected beam. So that you have to consider. So that only you have to think. So with that logic you can make solve the question.
So out. 4 options, which option will give you a better anti-reflecting film? That is the question.
Like that also it will come, but mostly it will satisfy only a particular wavelength. So by calculating itself, you can get that answer. So the same question, they don't need to give as a
Okay.
option also. They can directly give it as a numerical.
Okay.
And now you see, this is they are asking that which is the least thickness. Now you are seeing now some question which we solved now. This one. What is the minimum thickness there? You got 114.67 nanometer. This is the minimum thickness. Okay.
Yes, sir.
If if I am framing a question like this way, a soap film is surrounded by an air has a refractive index of 1.38. If a region of film appears to bright red in normally reflected light, okay, this is what is the minimum thickness there. They are asking. I am saying that soap bubble cannot be formed less than 500 nanometer thickness. I am saying like that way. So if it is a soap bubble, it will have a minimum 500 nanometer thickness. Minimum. Okay. It can have
Okay.
more than 500 also, but minimum 500 nanometer should be the thickness. But my soap bubble is giving similar condition. It is giving a bright red appearance. What should be the thickness of my soap bubble? What will be the answer? Because now you cannot take a lambda by 4 here, because lambda by 4 will give us 114.67. That is less than 500. So soap bubble cannot be formed less than 500 nanometer. That's a condition which I am giving. It's not a true, but I am saying. So what will be the next thickness? Where will have that constructive interference? That's the logic. You will get a 114.67 nanometer is a proper answer. That's true. That you understand. But I am saying that that is not possible. That is not possible because the soap bubble cannot be formed less than 500 nanometer thickness. Whether 114.67 nanometer is the only thickness which will give bright red color, or
No.
some another thickness also will give. What it will give? Now you have to see that. So if in your path difference, if you added an extra lambda, if you put an extra lambda, actually it is not going to give no effect. It will give the similar condition. Correct?
Yes.
Yeah. So actually you can add an extra lambda in the thickness. Even though I think, yeah, if this is like a, yeah, I'm just giving an example. Yeah, even though if you added a lambda by 2 there, it will give an extra path difference of lambda, because it is like a reflective thing, it's happening. But if you add a lambda by 2 there, 114 plus some 300 will come. 300 plus 114, it will give some 400 nanometer only. That also not give your thickness of your soap bubble, because I said that the minimum thickness should be some 500 nanometer I want. So actually you may have to add some full lambda there. So it will be like a 633 nanometer you might have to add with the 114.67. Okay. So 633 plus 114.67 will be some 700 nanometer. I don't think that much. That's a very thick soap bubble. But yeah, I'm saying that kind of question they can ask. I don't think they will ask this kind of
Okay.
complicated question. But the thing is that you have to know a thickness or a particular path length, plus you add extra path length of lambda. It will give the same condition. Add 2 lambda, it will give the same condition. Add 3 lambda, if you are adding extra path difference of lambda, it will give exactly the same condition. Similar way, on the face, you add 2 pi, it will give the same condition. You would add 3 pi, it will give the same condition. And sorry, 4 pi, you will give the same condition. The extra addition of 2 pi will give the same condition, because it will not change anything. Addition of a phase difference of 2 pi will not change anything. Similar way, addition of a path difference of a lambda will not change anything. Okay, this you have to care. Similar way, if you add a, yeah, path length should be lambda, addition will not give anything. But in that case also you have to check it. This is the path length of lambda. But in the case of like a reflection, sometimes it will go like 2 times. The path length will be a effect of 2 going and coming back, like 2 times of thickness or something. In that case, actually you don't need to add full lambda. Lambda by 2 itself you can add, such that when it is covering the entire path, it will be like lambda. That you have to see with your logic and other things. Got it? But the thing is that the condition will not change if you are adding an extra path difference of lambda. Similar way, the condition will not change if you add an extra phase difference of 2 pi. That's the thing. Got it?
Yes, sir.
So if you have any other concerns, yeah, because yeah, I was thinking that today I will take your feedback such that I can ask. So I can just tell what are the doubts which you got from your, or the confusions which you are having from your exam point of view. The thing is that it's an online based exam, so you don't know how the essay type questions are going to ask. Okay, this is one thing.
Yes, sir.
Yeah. So, and the next part is actually whether you are going, the question is coming in terms of Oslo as well as this programming with the Python and MATLAB. That's another question. Okay, next, other than this, yeah, whether any sample question paper is available, that's the third concern.
Ah, sir. Yes, sir.
Yeah, other than this, anything, any other concerns are available for this exam point of view, such
Worth
that,
of the question paper. Worth of the question paper.
but
Total marks.
total mark of the question paper. Okay, so yeah, how much marks the question paper will come. Okay, timing, that I think that will, anyway they will give during your hall ticket. Yeah. Whether you
Did
people,
anyone receive marks?
but
Did anyone in the group receive the house ticket?
I'm not getting.
I'm asking the other people also. Like, did anyone receive hall ticket? Like,
Okay, that you, that people can answer. I'm, so I didn't register for exam, so I cannot tell that. I did. I write this exam already as a normal coursework.
the other group people.
Okay.
Did anyone get hall ticket? Is what you're asking?
Ah, yes, yes.
No, I don't think they still got
Yeah,
the
yeah. I
hall
think it
ticket.
is taking some time. Yeah.
And sir, like, do you know any information on how the marks distribution will be there? Which week is more important? Anything like that?
That okay. That also I can. That
So
anyway
exactly.
I cannot ask. But yeah. But one minute. I'll check if anybody is typing anything.
And sir, will Oslo questions?
That I'll
Do
ask,
you ask?
but I don't think most of question will come in during your NSM exam. That I don't think, because that will be difficult for them also to process. Because you may be writing exam in some particular exam center, na, then
Yes.
there has to be also installed. I don't think. Only they are. I think they are going to ask conceptual based question and this numerical.
Numerical.
Yeah.
Okay, fine. Okay.
And yeah, that one, yeah, when I go through that exam pattern only, I saw that, yeah, they are saying that essay type question. So I will ask them that how that essay type question they are going to evaluate. It's like whether you have to type like paragraphs or something like that. I will ask.
Okay. Okay, sir. And this marks distribution also, like which
Ah,
week will be more important,
okay, that
uh,
I will ask, but yeah,
geometric optics or wave optics, the lasers or the Gaussian optics, which one will
oh,
be more important?
okay,
You know?
that I will ask, but yeah, usually if you are asking for the normal examination, that mostly faculties will say that everything is important. Yeah, but I don't know.
Yes, yes.
Yeah, I don't know what they are going to. But anyway, I'll ask that.
Okay.
Yeah. Any doubt or something in concern, you can say. No. Anyway, I think one more week is there. But that is a very short thing, na? Oh, yeah, actually, that week is over. Like, yeah. So this week is going to be over. Last week. So, but yeah, I
Sir,
will
I
take.
have a doubt.
Yeah.
I'm just searching the question, like in which assignment they have asked that question. Just give me a moment.
Okay.
Sir, can you just briefly explain me how to find aperture in any complex system, lens system?
Can you explain again? I'm not hearing properly.
How to find aperture or aperture stop in any complex lens system?
Aperture stop. Okay.
Yes,
A-
sorry.
Actually, I think aperture stop they will give. The thing which you have to make sure that
In assignment number 3, they have given the question.
were they given assignment.
Assignment week 3.
Just see. Assignment 3. This one. This,
Has,
this, this question you are asking.
not a particular question, sir. Like briefly, can you recap the things here if I
Yeah. Yeah. That I'm saying. Yeah. What will be the aperture stop? Aperture stop is the one which actually controls how much light is actually traveling through the system. Okay. So in this kind of thing, this kind of a complex thing. So I'm saying that I have two lens. Well, this two lens is actually not a complex thing. It's comparatively simple. Just think that there is I have a point source. Now aperture stop is the one which actually controls the amount of light which is passes through that particular system. Now, now just think that I don't have any two lens system. I have only one system here. Now just to say that which will be the aperture stop here. If there is, I didn't put anything here. What will act as an aperture stop here? Because I have a point source. Source of light is here. So this light will, or from here, the light will go any direction, like this way, 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 like this way. From this point, light will travel all direction. So actually, what is the one which is controls this light here? Just tell.
Lens one.
Lens. Hello.
Lens one.
Yeah, lens one. What is the property of that lens one? Lenses diameter will actually controls the amount of light. If this lens have a bigger diameter, it will allow more.
Diameter of the lens.
Yeah. So if there is,
Aperture.
yeah, if there is nothing available there, the lens itself will act as the aperture, and if the, that is the aperture which is contains the uh, if that controls the amount of light which passes through the system, then that will act as an aperture stop. Now I am saying that, now you said that lens one will act as an aperture stop here. If it's only the case in this condition, only lens one is there. Okay. Now I am saying that there are two lenses are there. So now I am putting like a two condition. My light is traveling from here, because anyway, because of the lens one, the maximum light which can go is this much only. This lens can be act as two. Sometimes it will converge. Let it be the converging lens only. So the distance is something like that way. It will converge light like this way. Okay. And after that, some divergence or something is happening. Now, which is aperture stop? Which is actually controls the amount of light which is passes through the system.
Lens one.
Lens one only. Why? Because if the lens two is also there, it is not at all used the whole portion of your lens two. Correct?
Yes, sir.
Yeah. Now another condition. Condition is something like that way. It is going like this way. Since it is going like this way, actually only this portion is actually getting passed through the system. Now, which is actually aperture stop? Now, which is aperture stop?
L1.
If L1 is the aperture stop, you have to get all the light which is passes from here to pass through the system. Now you see, because of the L2 is here, all the light, this much light is actually waste only. Okay, and this much light is actually
Okay.
waste only. And corresponding to this one, actually this light is actually waste. This light is also actually waste. So only the light which is passing up to this, only the light which is passing up to this is actually completely passes through the system. Even though the lens is controlling this much light, but this light is not at all used. This light is also not used because that is actually, it's not at all passing through the system.
Yes, sir.
So in this case, which is actually aperture stop?
L2.
Yeah. In this condition, actually L2 is becoming the aperture stop, because actually the L2 is the one which is controlling the light. Even though this much big lens is available here, actually there is no need of the size of the lens this much, because of this lens is this L2 is here, and the condition is such that this light is actually, that two lights are actually not necessary. So what actually controlling the light, which the uh, the thing which is controlling the light from here is actually L2. Now L2 is acting as an aperture stop. Got it?
Yes, sir.
Yeah. Now think that I am going to put a physical aperture in between. If my physical aperture is somewhere here, so let it be like a camera cover, and I have a camera hood like this way, and it has a entrance hole of this much big. In this case, which is aperture stop? Whether this thing has any effect here, this aperture has
No?
any effect here? No, na. So still in this condition, which is acting as aperture stop?
L2?
Yeah, here actually L2 is acting as an aperture stop. Now I have another hood which has a this much diameter, it's like a small hole hood. Now which is aperture stop? Now which will be the aperture stop?
Physical aperture, sir?
Yeah. Why? Because of that presence of the physical aperture is actually restricted all your light to passing through that system. Now only light which is actually reaching this portion is only passing through the camera, because after this thing, this light will not at all pass through the system. Okay, so only light which is passes through the system will be this one. So now you can see that even though that much big lens is not at all required, because there is no light here. Okay,
Yes, sir.
now you understand your concept of your aperture stop. So
Yes, sir. Yes, sir.
it can come anywhere. Now you see that this is the one which is controlling all the light. Now I am saying that I am going to put another aperture. It's not I am putting, it's like, yeah, that system actually have another aperture which is here. Then which will be the one which is controlling the light?
The second physical aperture.
Yeah. Why? Because that is actually from,
Narrow.
yeah, it is actually controlling, yeah, it's smaller only, it is passes through that one. Okay, so which is actually controlling the smaller, or which is the actually the which is actually controlling the amount of light can have anywhere in between the system, but you have to calculate the which is the one which is the least. So how you are going to calculate, that's another question. Now you understand the concept of aperture stop here. Now the
Yes,
question
sir.
is
Yes,
that
sir.
how you are going to calculate that one. So in the case of a, just think
Sir,
that, yeah, okay then.
In your previous diagram, that previous slide, uh,
Yeah, this one.
uh, if the second physical aperture width is same as the first physical aperture,
Ah.
then what will happen?
So there is no point of saying that this is the aperture stop or that is the aperture stop. And you are
Still L2 will be the aperture. So
which say you are
the
saying that
width of the second physical aperture is same as the width
uh,
of the first physical aperture stop.
okay,
Then
here
what will happen?
here you are saying here the
Yes, the second one.
physical width you are saying, or that just touching here you are saying.
No, no, physical width. The
Phys-
separation between the two.
yeah, that you cannot tell now. That's why I'm saying. Now I'm saying. Now I am saying that you are saying that physical width is same. So
Yes, sir. Same as the first one.
yeah, so I am going to put a aperture. This is width. Now your aperture width is same. Now just think that I am going to put that aperture at this position. Now width, physical width is same only, na?
Yes, sir.
Now say that which is the aperture stop here.
Uh,
Whether it is this your L2 is creating any, not L2, this A2 creating any effect here, because all the rays are actually not at all even touching that your aperture. It's actually in that position. Actually, it is it's not at all see, this light is not at all stopped by that particular aperture here. Now this particular condition I'm saying, correct, correct only, na? Hello.
yes, sir. Yes, sir.
Yeah.
Yes, sir. Yes, sir.
So which will be the aperture stop here, A1 or A2?
A1.
Yeah. Now I say, now you think, now I am not at all changing the width. Okay. Now I am moving the position of that particular aperture stop. Now I am moving that aperture somewhere here. Now also your physical width is same. This is the same physical width as here.
Yes, sir. Yes, sir.
Now which is the aperture stop? Now which is actually controlling? If it's A1 is only there, you see that particular light.
A2.
Yeah. Now if A1 is only there, the light is supposed to go like this way. But because of A2 is here, this much light cannot enter here, because only this is actually blocked here. So some actually it is made some more narrow portion. So only this much light will pass through that whole system. Even though this A1 is here, the entire light is not passing through that system. Actually, the so see that even the physical width of the aperture is same, but the position of that aperture is also actually matters.
Yes, sir.
Got it?
Yeah, got it.
Yeah. Now you got that concept of aperture stop. Now actually the question is how you are going to physically measure or calculate. So in that calculation, actually just think that only that normal thing. Now consider it's at only one lens. Okay, and one lens and one aperture system. I'm saying that this lens and this aperture system has the same diameter. How numerically you can calculate which is aperture stop? This both the lens and this aperture has the same diameter. how numerically you can say that which is going to be the aperture stop? By seeing this one, you just tell that which is aperture stop.
Lens.
Yeah. Why it is lens?
It has control over the amount of light passing through it.
Yeah. So lens can allow this much light. Okay. And this aperture can allow this much light. Okay. But even though this aperture can allow this much light, this light cannot even pass through the lens, so it cannot pass through the system. So the lens diameter is becoming the aperture stop. Okay, got it?
Yes, sir.
Yeah. Now you can actually see how you can measure. Now you are getting an idea of measuring that which is the element which is going to be an aperture stop. Now see, this is actually making an angle of some theta 1 here. This is making an angle of theta 2 here. Now see which is making a least angle. That will be the aperture stop. Got it?
Yes, sir.
Yeah. Now just think that I am reducing the diameter of that particular aperture. Now, which will be the aperture stop?
Physical aperture.
Yeah. Why? This lens,
It
if
has a
yeah, if there is no physical aperture is here, the lens will make this much bigger angle. But because of the physical aperture there, it can make a angle this much only. So which angle is bigger? Theta 2 will be here, theta 1. Which is the bigger angle?
theta. Which one is theta one?
Theta 1 is the one which is making with the lens. Theta 2 is that one with the making with the aperture.
Theta 2 is smaller.
Yeah. So always check which angle is the one which is a smaller one, and that will make a aperture
Stop.
stop. Now another concept. Now you are going to put a physical aperture here. Okay. You are going to put a physical aperture here. Whether you can use the same, can you just think that this will be that angle which is making by this one? Whether it can be take it as a, some theta 3?
Pardon me, sir?
Now you put a physical aperture here, na?
Yes, sir.
Yeah. And I am directly drawing one line from my source to your physical aperture, and I can describe this angle. Whether whether this is a good method or not.
No, sir.
Why? Why it is not a good method? Because here actually for this lens and this your first aperture we have only directly drawn and see which
It's
is
going
smaller.
to affect the angle.
But
Lens is going to affect the angle.
yeah, the lens there is a one powered element is there in between. So you don't know the light is going to pass like a straight line or a bent portion. Almost we are almost sure that it is going to be a in the form of a bend only. So now you have to think how it will be look if you look from this side. So we have to look from this side, and we have to see how much we are seeing it as a this aperture stop. So what we are doing, we are looking an image of this particular physical aperture by this L1, and if that image is something like a bigger one, we can say that okay, it is forming some bigger image by the lens. So we can, for to that image actually I can draw, because the image is formed by the lens. Okay, so if you are looking an aperture through a lens, actually you have to look it as the image formed by that particular lens. Then only you can calculate that particular angle made by that image. From the image you can actually draw the line, because that image is formed by that lens. So if your physical aperture is coming at that position, you have to take the image of that aperture formed by the lens before that one. If you are measuring your, what you called it, uh, the two peoples are there na, yeah, entrance people. If you are going to measure it as an entrance people, you have to see how it is appearing as the, from by the lens which is at the left side. Okay.
Okay, sir.
Yeah. So this is the way you have to calculate it. So if the some powered element is coming, you have to see the effect of that powered element, means the lens, and you have to see how the image is getting formed by that particular lens, and only based on that image you have to draw your angle. And if that angle is coming smaller, then that particular thing will be act as an aperture stop. If that angle is coming as larger, then you don't need to worry about that one. That will not be aperture stop. The previous thing will be the aperture stop.
Okay, sir.
Got it?
Yes,
Yeah,
I got it.
yeah, this is the way you have to calculate. Okay, if you have a doubt,
Can I ask another question, sir?
of course you can.
The matrix,
It's a
matrix
matrix. Ah, yeah.
assignment number
1 minute, I'll just go. Assignment number
4.
4. Let me take that. This one.
I wanted a brief explanation related to matrix, sir, like how you explained about aperture.
Okay. This explanation, I think it will take some time. So you have to do what you are going to do. You're actually making a lens, I think, here. D1, D2, DF. Yeah. What you are defining, you are going to define a, there will be some particular lens or an optical system. It's a combination of different lenses. Okay, got it? There can be
Yes, sir.
a lens or an optical system, or it's a combination of lens or a thick lens. So I'm saying that this will be like a, a system. It can contain multiple lens and other things, everything. Now actually you are defining two distances, d1 and d2, and you are saying that if you define this d1 and d2, and based on the properties of your system, if this combination, the d1 d2 combination, can act as a thin lens approximation of your system. So your system will have a lot of elements. It will have a translation system, like it can be a thick glass slab, or it's a path of light which is passes through that lens, or it will have some curvature which is having when it is coming to an interface. So when your system is going to be complex, so if you want to solve the system, what you have to do, you have to go what are the elements of the system, or what are the length it is passing through the system. You have to go through each interface as well as each translatory system, and you have to solve what happening to each ray, whether the ray is bending or ray is passing in the same way, how much angle it is getting bent, like that way you have to check. Then only you can get a total tracing of your matrix, tracing of your ray, I can say. Okay, that's true.
Yes, sir.
Yeah, but that will be a cumbersome task. That will be a difficult task. Means you have to put your all lot of effort in that one. So what we will do, you will define two distances. You will calculate the whole parameter of this thing, and you say that this is a black box. This is a system containing a black box which will have two distances, some d1 and d2. For this d1, including this d1 and d2, the whole system will act like a thin lens, you will say. So the whole complex system actually you can consider as a thin lens with your imaging condition, such that you don't need to much worry about your complexity of your inside system. What you did, first you have to go through all the properties of your system and define two distances at the either side of the system, such that including that distances, the system will act as a, will obey a thin lens approximation. So if you solve that system, if you solve the system, actually you are going to get a particular matrix for that whole system. See, 1 d2 by f. This f is actually that this is a simple system containing a lens. Okay, similar way here you define your d2 f minus 1 by f, like a d1 plus d2 minus d1 by d2 by f, like that way. So you are going to give a matrix for that particular lens or particular system with a particular focal length, such that it will actually behave like a thin lens. If you put it is like a thin lens, what will happen? If it is like a thin lens approximation, you can actually, now you see, these are the properties. You are seeing one f here na, and that one lens here.
Yes, yes, sir.
this this lens is not actually a physical lens. This can be a system of lens. Okay,
Okay, sir.
and with that particular system, actually you are going to define two principal distances, and it will act like a thin lens system. So yeah, for going to that one, actually, yeah, you can, you have a, for, for arriving this one, actually you have to reach that different matrices. So yeah, this will be like a little bit involved thing. This actually I told to people, like when you have to go through this here assignment. So to understand this one properly, what you have to go, you have to go through the translatory matrix and the matrix corresponding to that mm, curved surface, then matrix corresponds to lens, and yeah, I think these three things. Mirror also is good, but yeah, translation, refraction, refraction through curved surface, refraction through lens, and yeah, this, yeah, these four things if you went through, actually you can actually get the idea of these things. It is a little bit involved thing. Yeah, it's better you spend some time on this one, that will be good. The main idea is like that way you will converge a complex system into a thin lens approximation, such that it will directly follow the lens maker's rule kind of thing, like 1 by d plus 1 by d1 plus 1 by d2 become 1 by f kind of thing. So it will be like a, it will make your life simple, that's the thing. But yeah, put some effort on that, it will be easy, it will not be complicated. But yeah, since it is matrix is involved, yeah, you may have to do some matrix multiplication and taking conjugate and other things kind of thing, you have to do that only. But yeah, the idea is simple. You have to make a complex system into a thin lens approximation. For the what one, for that what you can do is the involved calculations. But yeah,
Okay, sir.
you have to spend some time on this one, that's true. Yeah, any other doubt?
So far, I had these doubts, sir. If any other doubts are there, I will
Okay.
tell you, sir.